Good morning. So today we're going to talk about the geometry of molecules. We'll be able to draw a molecule on paper and then compare it to how it would look like in real life. And to simulate that real life appearance, we'll be using a model kit. All right, this is the Molymod brand. I'm not paid to use or endorse this or anything, but that's the one I've kind of gotten used to over the years. Molymod, Molymod is the brand. All right, so yeah, once we draw them correctly and build the models correctly, we'll be able to figure out bond angles and things of that nature. All right, the first thing we'll need to do is let's just use these 6 example molecules today, and we're gonna build Lewis structures with them like we did in the previous video. Once we've done the business as usual sort of Lewis structures, then we're going to analyze each structure and then figure out how to think of them in 3D. So the 3D part will come later. Let's just do a review of these Lewis structures. All right. So if you've done these before from the previous video, then you can kind of skip along. But otherwise, here's a review. All right. So we got methane, 1 carbon, 4 hydrogens. And so that's going to be, get your valence electron sheet handy, also known as a periodic table. All right. Carbon's in the 4 column. Hydrogen is in the 1 column. All right. So 1 times 4, 4 times 1, 4. 4, add them up, we get 8. Carbon in the middle. Spend 2, spend 4, spend 6, spend 8. We have spent all 8, and this Lewis structure is done. All right, on each of these sheets, I'm going to leave some room on the right side of the sheet to do the second half of the video today, which is the geometries. So that's methane. Now let's go to ammonia. 1 nitrogen, 3 hydrogens, 1 times 5, 3 times 1, 5, 3, adds up to 8. Nitrogen, hydrogen, hydrogen, hydrogen. We have spent 6. 2 more left to spend. Hydrogen's happy on the outside. Nitrogen needs 2 more. We have 2 more. And so now that molecule is done. Ammonia. Water. Done. CH2O, formaldehyde. Plus 2 plus 6, that's 12. Done. Sulfur dioxide. Done. Lastly, carbon dioxide. $16. done. All right, we've done all 6 molecules. And again, these are reviews from the previous video. All right, great. So let's go back to the beginning. We'll start with methane. Now that we've done all the Lewis structures, what I want us to do is analyze the central atoms of each of the molecules. I'm talking about the central atom here, not the outer atoms. All right, and what we're going to be looking for is we're going to be counting the number of atoms that are bonded to the center, and we'll be counting the number of lone pairs on the center. All right, so I'll just call this a central atom, a center atom, central. I can't decide which adjective to use. Center atom analysis. Yeah. All right, and so looking at a center, that one, I want us to count the number of bonded atoms. We can just write number like BA for short. And then the number of lone pairs. Number of LP for short. All right, so on the central atom, carbon, we see that there's 4 atoms bonded, those 4 hydrogens, so we're going to put a 4. And we see that there are no lone pairs on the center atom, so we have a 0. So I'm going to call this a 4-0 structure today, 4-0. I'll show you what I mean with that later. Let's just have this count done for each of the central atoms, and then we'll refer back to what this actually means. All right, so ammonia. Here's our central atom. Number of bonded atoms, number of lone pairs. We can see there are 3 atoms, these 3 hydrogens, 1, 2, 3, bonded, and we see that there's 1 lone pair right there on the central atom, the nitrogen. So this is what I like to call a 3-1 structure. All right, how about water? All right, hopefully you see 2 bonded atoms, the 2 hydrogens, and 2 lone pairs. Okay, we don't count the central atom itself, we just count whatever is attached to, whatever is on the central atom. So water is what I like to refer to as an example of a 2-2 structure. Formaldehyde. Here's our central atom. 1, 2, 3. We have 3 bonded atoms. And lone pairs, we have 0 lone pairs. Okay. Don't put 2. Indeed, we do have 2 lone pairs, but they're on an outer atom. So that doesn't count for this central atom analysis. Carbon itself, the central atom here, has no lone pairs on it. 3, 0. 3 for the oxygen and 2 hydrogens, no lone pairs on the carbon. Sulfur dioxide. All right, sulfur, there it is. 2 atoms attached, 1 lone pair on the sulfur. There it is. All right, I know some people like my color coding, so I'll just slow down and maybe get some of that done. Sorry, I got all these papers around. All right, so here's my bonded atoms for that count. There's my lone pair for that count. Cool. And then lastly, carbon dioxide, central atom. All right, we got 2 bonded atoms, the 2 oxygens, and we have no lone pairs on the carbon. So this is what I would call a 2-0 structure. All right, let's make sense of all of these numbers. Okay, so to make sense of all these numbers, I want us to build a reference table together. All right, or maybe should I call this a table? Maybe it's just a collection of pictures. I'll let you decide what to call it, but maybe before you start writing this yourself, you should kind of see how I do it. Well, let me tell you what I'm going to do. I'm going to have a total of 6 pictures here. I'm going to have one here, here, and here, here, and here, and then there. And I'm going to try to leave plenty of space around the pictures, as well as like here, so that I can put commentary later. But sometimes I like to start with the pictures before I actually describe what I'm having y'all do. So here's my first picture. All right, and then here's my next one. And then here's my final one for the first row. Sorry, allergies, man. Okay, so that's my first row. Here's going to be my second row. All right, maybe you might be having an idea of what I'm getting at now. Maybe not yet, we'll see. All right, there you go. There are my 6 pictures. All right, take a minute now and copy these down. Oh, hang on, before you copy them down, I forgot to put a lone pair right there. All right, now you can go ahead and copy them down. All right, hopefully that was enough time for you to copy them down. So what I want you to do now is circle the central atom on each of these pictures. Well, I guess you don't have to circle them, but I will. All right, so these are like wireframe drawings. Each of the darkened spheres represents an atom, and each of the lone pairs represent lone pairs. All right, and so basically what we're now going to get at is this. In Chem 101, there are 6 basic shapes that we cover. Every molecule in the class will fall into one of these 6 shape categories. Every single molecule we did today, the 6 we did today, fall into one of these 6 categories. The way I chose the 6 molecules is that each molecule will fall into one of these 6 categories, and I made sure that in choosing the 6 molecules, each category is represented once. Okay, so I'm going to want us to take the 6 Lewis structures and place it into each of these categories. So to help with that, before we do that, let's just look at each of these drawings and let's count how many bonded atoms there are with the first number. So in this one, 1, 2, 3, 4. And then how many lone pairs? Well, 0. So this is a 4-0 structure. How about this one? 1, 2, 3 bonded atoms, 1 lone pair. This is a 3-1 structure. Here, 2 bonded atoms, 2 lone pairs, 2-2 structure. 3-0, 2-1, 2-0. So now that we've done that analysis, go ahead, take a minute or two, and take the 6 example molecules we did earlier and place them next to these names. All right, I'll pause here. All right, so let me show you how I went about this. I'll use this teal turquoise color here. So methane, we saw was a 4-0 structure. So I'm gonna write methane right here, CH4. All right, ammonia we saw was a 3-1. NH3. Water, a 2,2. I need like anti-slip grip on this table or something. All right, formaldehyde, 3,0. CH2O, there it is. Sulfur dioxide, a 2,1. 2,1 structure. And then lastly, we got carbon dioxide, a 2,0 structure. All right, we are getting closer. All right, so it's usually around this point someone may notice, hey Josh, I kind of noticed something. These two numbers add up to the same number every time when we're in this row. That is to say 4 plus 0 equals 4, 3 plus 1 is equal to 4, and 2 plus 2 is equal to 4. So everything in this row has 4 things total. Is that intentional? Yes, it is very intentional. So we can make a new column, number of things. And everything in this row has 4 things. Okay, and by things, very scientific word, right? By things, we mean either bonded atoms or lone pairs. All right, the technical name for a thing is called an electron domain. Okay, domain just means a location, and electrons meaning electrons. So an electron domain just means a place where you can find electrons. You can find electrons on atoms that are bonded. You can find electrons on lone pairs, which are literally electrons. Okay. So that's our count of things. All right. And if we continue that analysis, everything in this row has 3 things, 3 electron domains. 3 plus 0 is 3, 2 plus 1 is 3. And there's only one possible scenario for having 2 things, all right? A 2 plus 0 situation. Okay, so we can kind of categorize these in bubbles. Okay, let you catch up. Cool. So we can see that even though we have 6 total scenarios, we actually have 3 subgroups of geometries. All right, and the first subgroup has 3, the second has 2, and the last one has 1. Let's start out looking at this subgroup with 4 total things, 4 total electron domains. All right, so I'm going to show you how to use these model kits. All right, be ready for a lot of popping sort of sounds. Okay. So you get a model kit. You're going to have different sorts of tools available. There might be a color code for different types of atoms. Carbon is often chosen with the black atoms, because if you think of like graphite in a pencil, black, grayish sort of color. Coal is black, so on and so forth. So here's our carbon. And then you'll see different types of bond options. Ooh. All right, these curved bonds will be used later to make double or triple bonds. That flexibility will come in handy. And then these shorter bonds will be used to make single bonds. Now you may already know that double bonds and triple bonds are actually shorter than single bonds. All right, if you haven't heard that yet, well, now I'm telling you. So you may be thinking, well, why is a double triple bond longer? You'll see later that we'll fix that issue. So we won't worry about that. So use the thick bonds for the single bonds. All right, so we'll connect hydrogens, the white ones. And I've already done that for some of my hydrogens. Nice when it snaps easily. All right, and now we have methane. All right, we have CH4, methane. Okay, or as some people say, methane. So let's look at our methane. Okay, hopefully it looks somewhat similar to our drawing here. And if you have your own model kit, great. Let me put this paper away. So one thing I like to do and have students do, this is kind of easy doing the camera. You can see if I have it right under the camera perfectly, that we have like perfect, equal, even angles everywhere. All right, I can hold this here and I can kind of rotate here, but I get the same result. Same result, etc., etc. So all the angles here are exactly equal to each other. Okay. This shape that's going on is called a tetrahedron. A tetrahedron is an example of, I think the mathematicians call it a platonic solid. That's when each side is exactly the same shape. So we have an equilateral triangle here, right here, that's called like a face. Okay, and then we have another equilateral triangle face of the same size. And we have 1, 2, 3, and then upside down 4. Oh, there, 4. All right, so 4 sides, tetra. Tetra means 4. This is a tetrahedron. Okay, and then you can have like an octahedron. Octahedron is 8 sides. All right, but we don't have an octahedron here. This is a tetrahedron. All right, so anything that has 4 things on it will have a tetrahedron shape. So we're going to call that the tetrahedral family. Okay. And so some people call that a parent geometry, a PG. And that would be tetrahedral. Okay, so everything in here has a geometry that's called a tetrahedral geometry, having 4 things on it. Let's build the other molecules in this tetrahedron family, or I already did that. Okay, and so here's ammonia, and then here's water. Okay, let me take this distracting paper away. These are 3 very different molecules in a common sense sort of way of thinking about it. Methane is the main component of natural gas. It's a fuel. Ammonia is a precursor molecule for making synthetic fertilizers. All right. This is a gas, also a gas, but can be compressed to a liquid a little more easily. And then we have water, which of course is a liquid at room temperature. All right. So we have a fuel, we have a fertilizer, and we have the solvent of life. Yet, today I'm arguing they have more in common than you would think. And what I'm getting at is, look, it's the same shape, same tetrahedral shape each time. But instead of having an atom here, we have a lone pair. So some model kits, they have this bubble tool to show that you have a lone pair. All right, and what some students, not many in my experience, but what some students like to do is, like, whenever they have a lone pair, they like to draw a bubble on it. Again, you don't have to do that, but feel free to do that. All right, and then water has 2 of the bubbles on it. All right. All right. So regardless of you have bonded atoms or lone pairs, you get that same parent geometry. All right, I want you to see that the bond angles here are the same every time. Okay, we have an angle right here, right here, right here. Okay, it's all the same angle. And those bond angles in the tetrahedral family bond angle is 109.5 degrees. 109.5 degrees. Okay. It's not 110. It's not 90. It's not 105. It's 109.5 exactly. All right. There's a mathematical proof out there that exists of it, or you can just do bond angle measurements if you're a chemist. But 109.5. All right. This number I find so important that I often joke that if I had my own radio station, it'd be KHEM. Okay, here in the United States, if you're west of the Mississippi River, you get a K in front of your TV or radio station. All right, if you're east of the Mississippi River, you get a W. So KHEM for chem, that'd be 109.5 degrees, or we could be FM, whatever. Okay, that's my radio or TV station. Okay, 109.5, KHEM, 109.5, traffic and weather report. All right, so that's the tetrahedral family. All right, next up, we have this scenario, having three groups. Okay, so I pre-built some of these molecules already. All right, give me a moment to fetch them. Actually, I didn't have them pre-built, so I had to pause the video. I'm low on, whatever you call these. I got this from a thrift store, so it's probably missing some things. So, all right, so here's my formaldehyde, CH2O, carbon, hydrogen, and then oxygen. All right, and this is where those double bond tools come in, those bendy ones, all right? So by having them bendy, you're able to connect two bonds to it, and then you end up with that double bond, all right? So carbon, oxygen, double bond, and then two hydrogens, and then we get this sort of shape, all right? Back when fidget spinners were popular, people would call this the fidget spinner shape. Okay, I broke my fidget spinner. I don't have one. Or kind of like a peace sign, all right? Peace, right? And similar thing here, except we have a lone pair up here on the sulfur for sulfur dioxide. But we get this same sort of flat peace sign fidget spinner shape. All right, and we're gonna have 120 degree angles in between. All right, so this family is gonna be called, it's a mouthful, Trigonal Planar. All right, Trigonal Planar family, that's gonna be our parent geometry, Trigonal Planar. And our bond angle here is going to be 120 degrees. All right, so that's the Trigonal Planar family. Trigonal meaning triangle, planar meaning flat. And then lastly here we have carbon dioxide. Okay, carbon, here's the first double bond, here's the second double bond, and it forms a straight line. So that's going to be easy named. As parent geometry is called linear. Okay, it's a straight line, and the angle, well, it's perfectly horizontal. So we have a 180 degree angle. Okay, so if you're keeping inventory of angles today, we had three possible angles: 109.5, 120, 180. Okay, cool. Hopefully y'all are with me so far. Now, I want to talk about something else. All right, some will notice at this point, and I'm happy when you notice it, I wonder if there's like some sort of mathematical pattern going on. All right, you may be thinking, okay, we got 360 degrees in a circle, and we have two things. So we divide by 2 and we space it out evenly. Is that where 180 degrees comes from? Yeah, you're right. That's awesome. All right, so on that same pattern, you're like, oh, okay. 360 degrees divided by 3. Is that where 120 degrees comes from? Yeah, you're right there too. Good. Okay, but then Josh, what on earth? I got 4 things, 360 degrees divided by 4. That's 90 degrees. So what the heck? How come that's not 90 degrees? How come that's 109.5 degrees? So glad you asked. So to answer that, we're going to have to bust out this crazy slide. All right. Hopefully I can make this less intimidating with a few minutes of talking about it. All right. So we got to talk about this doohickey called VSEPR. VSEPR. All right. So VSEPR, I put a CA in front. I'll explain what that means in a minute. All right. But VSEPR, when you're taught VSEPR, it stands for Valence Shell Electron Pair Repulsion Theory. It's a theory. All right. And that's a mouthful. Let's demystify that. So valence shell electrons, that just means we're talking about valence electrons. Okay, yeah, I know valence electrons. Those are the electrons on the outside we've been talking about forever. Yep. And valence electrons, they occur in pairs. Like bonding electrons occur in pairs. Lone pairs occur in pairs. So electrons, when we're talking about bonding, occur in pairs. Okay, so we're talking about valence electrons occurring in pairs. Okay, that's not too bad. And then we got this other word, repulsion. Repulsion. Why are we talking about repulsion? Well, this will explain geometries in the VSEPR world. So in the VSEPR world, we pretend everything hanging out on the central atom, whether you're a bonded atom or whether you're a lone pair, we pretend everything has a negative charge on it, right? And that central atom acts as the pivot point for all repulsions, okay? So let's start with something like carbon dioxide, right? We're going to now ask a question from a repulsion point of view. Why is carbon dioxide a straight line? How come we don't see something bent like water, okay? How come it straightens out? And the idea is going to be, well, we're bonded to the central atom, and the central atom is where we can pivot. All right, so I don't know if this will get on the screen. No, I don't have enough space here. Okay, so I can't do it with my arms, so I'll do it with markers instead. So we'll pretend we have the central atom right here, okay, at the middle point. And if my marker caps are the outside oxygens, my outer atoms, as I bring them closer, ooh, they're going to start repelling. Oh, this is better. I should just have been right here. All right, they're going to start repelling. So it's like, okay, time to go the other way. All right, this is pretty good. But what if we start going too much the other way? All right, repel. So the happy medium would be right here in the middle, a 180-degree angle. That makes these negative marker caps or atoms as far away from each other as possible. Okay, and the idea is with VSEPR, that's what atoms are naturally going to do. They're going to naturally arrange themselves to the most stable position. Okay, here, can I do this with my hands? So it just kind of levels out right there. Okay. So that explains the linear shape when you have two groups. Okay, what if we add a third group? Now we have 90 degrees here and here and 180 there. So we're going to need to spread this out. And we can't go too far because otherwise we have a problem right here. Okay, so we end up with 120 degrees. All right. And it's not like we should be going like forward or backwards, because like if we go forward here, we now have a 90-degree angle right there, which is not as good as 120. So that means if you have two groups, you're a flat molecule, you're linear. If you have three groups, trigonal planar, you're still a flat molecule. You don't need a front and you don't need a back. But if we go to 4 groups, then yes, we do. See, at the moment, we're thinking like a circle. So it's like 90, 90, 90, 90. But by using a front and back for the molecule, we are able, this is too hard, I'm just going to do it with my hands. Okay. All right, so like 90 right here, and then my legs are 90. Okay. But what the molecule ends up doing is twisting and then going front and back like that. All right. So instead of being flat like this, 90 degrees, the molecule figures out, oh, I can use space above and below. And by going 3D and using all the space around me, then I am able to minimize repulsions more. Instead of a sharp 90-degree angle, we have a more obtuse 109.5 degree angle, and that is what nature decides to minimize repulsions. All right, so that's VSEPR. VSEPR does often a very, very, very good job of predicting geometries, anywhere between, I don't have the exact calculation, but I would guess roughly between 70% accuracy to even sometimes 100% accuracy on those angles. This is all done with repulsion-based arguments rather than taking 3 or 4 semesters of calculus, maybe some linear algebra, maybe some partial differential equations using a supercomputer or some nice software package and calculating those angles. We see that this VSEPR idea will often agree decently well to very well with experimental findings on angles. So pretty good. And this is especially true for carbon-containing compounds, and of the roughly 10 million unique chemical formulas out there, 90% of them contain carbon. I'm not saying 90% of the elements out there are carbon. No, that's not true. The most abundant element in the universe is hydrogen. But of the unique ways of arranging chemical compounds that we know on Earth, 90% of those unique arrangements contain carbon. And a lot of the things we just talked about with VSEPR hold true for carbon. So we can predict a lot of geometries pretty well with this nifty little VSEPR trick. Cool, we're almost done. The closing note here is we've done most of the important work on the geometries and the angles. But some Chem 101 intro chemistry curriculums will teach a second vocabulary piece for geometries, and that's called a molecular geometry. All right, me personally, I find the parent geometry names to be way more important, but because it's expected in a lot of 101 curriculum, this other geometry called molecular geometry, I'll go ahead and teach that as well. Okay, so this first number, I think I used red earlier, the number of bonded atoms. Let me go ahead and box each of those in red. And let me do the same for the lone pairs with blue circles. Okay, and then we're going to write out these molecular geometry names. So the molecular geometry okay, well, let me color code it here. So the parent geometry, I'll have it in green. And then the molecular geometry, I have red out, so we'll just use red. I'll use in red, okay? What on earth is a molecular geometry? A molecular geometry is when you think of what a molecule looks like if you made all the lone pairs invisible. I didn't take away the lone pairs. They are still there. I just made them invisible. And then we get this idea of molecular geometry. So if we look at the first molecule, CH4 methane, there are no lone pairs on the central atom, so it still looks like a tetrahedron. So therefore, its molecular geometry name is a tetrahedral as well. I'll just write tet for short. So something like methane, its parent geometry is tetrahedral. That's the family. Its molecular geometry is also called tetrahedral. Whenever you have a molecule with no lone pairs on it, the parent geometry and the molecular geometry names will be exactly the same. All right, now let's go to ammonia. If you look at ammonia, okay, still a parent geometry of a tetrahedron. But if we clicked this to be invisible, it's still there. We can see that our molecule looks like a pyramid. Okay, we have a triangular base, and then we have a pyramid. It's a pyramid. You can slide something underneath, and you can see that there's space underneath. It is a pyramid. It is not flat. It's not trigonal planar. It's not like a fidget spinner or peace sign. Okay, it's in 3 dimensions. So that name for that molecular geometry is called a trigonal pyramid. Trigonal, Trigonal, pyramid, Pyramid. All right, and then our last molecule here's water. You put invisibility on water, you get this bent shape. It doesn't magically become linear, okay? I didn't take away the lone pairs, I just made them invisible. The lone pairs are still there repelling these atoms down so that instead of being linear, it's a bent structure, okay? So a 2-2 structure is what we would call bent. Sorry, this is getting a little bit cluttered. When I practiced this, it looked a tad better, but that was a while ago. All right, cool. So let's keep this going. Molecular geometry here. This would be called Trigonal Planar. I allow my students to just keep it shorthand like trig plan. This would be like trig pier, trig plan or trig plane. And then this is actually also called bent, the SO2 example, a 2-1 structure. I would accept, me personally, bent for an answer here or there. Some instructors might like to make a distinction, like, please call this 109.5 bent. Please call that 120 bent. But they're both bent. Like, here it is. I took away the lone pair, and it looks bent. But you can tell the water bend is more of a sharp angle, 109.5, compared to like the 120-ish happening over here. All right, and then lastly, we have carbon dioxide. Well, no lone pairs, so this molecular geometry is also linear. I know it causes a lot of anxiety to have 2 possible different names for any chemical structure, okay? So to keep it simple, a few tips. Remember that you have 3 different families, okay? So long as if you have 4 things, your parent geometry and also your bond angle will always be exactly the same, tetrahedral, 109.5. 3 things, trigonal planar. 2 things, linear. And because half of the 6 examples have no lone pairs, that means for half your examples, the 2 different possible names are exactly the same word, actually. Same word, phrase, same phrase. So it's only for 3 geometries that you're going to need to know that there's a different name for the molecular geometry. And it just got better because for 2 of them, we just call it bent anyways. So if you were forced to guess, bent is not like too bad of a guess. There's only one molecule here where the 2 names are different and it's not a bent, and that is this trigonal pyramidal like we have for ammonia. All right, so a few closing things. All right, closing thought number 1 is when it comes to the 6 geometries, I am a strong advocate for students having an example structure for each of the 6 geometry cases memorized down pat, memorized perfectly. And that way you can always reference that for all the information. For me personally, these are my 6 favorites to keep in mind, which is why I shared them with you. All right, so that's point number 1. Have an example molecule for each case. You can have more than one example if you want, but at least one. Okay. The second thing is, depending on your instructor, I don't know how important your instructor would find this, but I imagine some would, which is how to draw these sorts of molecules. So these structures, I didn't try to do anything too much to try to make it look like 3D on paper, but there are ways to do that. So that's how I'm going to close this video. Okay. We're going to try to draw in 3D. Okay. Let's take methane as a start, CH4. I think it's easiest to draw in 3D often when you make as many things as possible not in 3D. So holding it this way, I have carbon right here, this hydrogen and this hydrogen flat in the plane of the paper. So in other words, then I only have this bond and that bond to worry about representing in 3D. So this one, the way I'm holding it is popping out at me. This one, this hydrogen is popping away from me. So I'm going to try to go like that. And then for this carbon-hydrogen bond, it's sticking out at me. We're going to use something called a wedge. Okay, like a pizza wedge. Pizza wedge? Pizza slice? Never mind. And then for this one, going away from me, I'm going to use something called a dash. Kind of make a tornado. Or some people like to go choo, 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 choo. All right. So yeah, wedge. And then dash. Okay. And the way we try to make you think or see that the wedge is getting bigger is it starts small and then it gets bigger as it goes out. And the idea there is as something gets closer to you, it appears bigger to you. Opposite idea for dash, as something's going away from you, it appears smaller, more out in the distance. Okay, so that's one way you could draw methane. Some people like to kind of do the this way. So it's like kind of arms going like that. All right, that could be maybe another way of drawing methane. All right, some people think of something like that or something like that. Maybe I'll do one more. And then one hydrogen kind of popping out. So kind of, yeah, like that. Okay. I find this easiest, personally speaking. But they all mean the same thing. All right. And then let's do something like ammonia. I like to use the same tetrahedral skeleton here. And then keep my lone pair up top so I don't have to think about it in 3D. And if you like the bubble, there's your bubble. All right. The only 2 cases of molecules where you have to draw in 3D for a 3D drawing is tetrahedral and trigonal pyramidal. For anything else, you don't have to draw in 3D. Not even for water. Like water, you may be thinking, well, it's in the tetrahedral family. But look at its atoms. They're bent. Okay, it's bent. We don't have any atoms that we have to draw in 3D. I mean, if we held it like this, I guess you could draw in 3D, but we don't have to. So for something like water, it is perfectly acceptable to do something like that. Or some people like to draw water like that. And anyone who's taken chemistry, they'll usually understand these two to mean the same things. If you really wanted to like draw it in this 3D orientation, okay, fine, you could. To really make it look like a tetrahedron, okay, sure. But again, you don't have to. Okay? And yeah, the other structures, you would not have to try to make an attempt to draw them in 3D with dashes and wedges because you don't have to. Okay? They're flat, so you don't have to do that if you don't want to. All right, I think that is enough for one video. I hope that was really helpful. I hope you found it helpful to make your own VSEPR reference table. We'll finally have a title for this. You made your own VSEPR reference table, and hopefully you kind of felt the bonds and the geometries rather than just reading a paper and trying to make sense of it. So again, hope this helps. Any questions, comments, suggestions, let me know. I hope you have a great day. Take care.